last week we started to discuss the extreme value theorem. We got to a statement of the theorem, and we had two graphs which I didn't fully describe. But let's recall the statement of the theorem. The extreme value theorem says if f of x is continuous on a to b, all we need is a continuous function, a curve that connects all the dots in a sense in one consistent manner. Then f of x attains an absolute maximum and an absolute minimum somewhere on that closed interval. And remember, an absolute maximum is a highest point, a largest y value, and an absolute minimum is a lowest point, a smallest y value, somewhere on this interval a to b. And, well, you may ask yourself, well, what if it's an open interval? This statement assumes it's a closed interval. What happens if it's an open interval? Well, we'll see in a moment that that's not necessarily true. But we had these two curves over here, and I probably wrote something like observe right before them. But these two curves we did start discussing last week, but we will further clarify this right now. Observe, we have two functions here. Notice this one is not differentiable because it has a point up there. Not differentiable everywhere because it meets at that corner. This one is. But they're both continuous. And in both cases, we've blocked off an a to b. And I'm going to shade in the portion of the function that this blocking off corresponds to. So in the first case, piece of the function on a to b is something like that. And in the second case, it is something like that. The extreme value theorem says if we have a continuous function on a closed interval, then there is an absolute maximum and there is an absolute minimum. So with these two curves, that should be the case, and it is the case. What is the largest y value here? Well, I didn't mark off any y values because, for these, just observations, throwing numbers on the y value just added clutter to the graph. But what is where is the highest y value achieved here on this closed interval? Not the entire function, just a to b. The largest y value occurs at point B. It's whatever that y value is. So here, in the first case, the absolute maximum occurs at point B. It occurs at an endpoint of our interval a to b. So I'll note here, the absolute maximum, which we can abbreviate ABS, MAX. Here, the absolute maximum occurs, I'll say, do I want to say at B or at an endpoint? I'm going to say at an endpoint. Here, the absolute maximum occurs at an endpoint, meaning it occurs at either A or B. Here in particular, it occurs at B, comma. So here, in this case, the absolute maximum, the largest y value, occurs at this endpoint. What about the absolute minimum? Where's the red and blue chalk? It's all the way over here. The lowest y value that's achieved is hit at that bottom of the curve. So the lowest y value occurs down here. It's whatever that y value happens to be. But in particular, the absolute minimum here occurs at a point where the tangent line is horizontal. It occurs at a point where the derivative is 0. So, and the absolute minimum occurs at a point where the derivative is 0. That's a lot of words. Occurs, I guess I can't avoid that many of those words, at a point where, I'll just say f prime equals 0. So the largest y value occurs at an endpoint in this case, and the smallest y value occurs at a point where the derivative is 0. Any questions about that first observation? Okay, now what about the second one? Well, let's start with I guess we'll start with the absolute maximum since that's how the sentence went. The absolute maximum here occurs up at this corner point. And remember from one of the lectures last week, if we have a corner point, then the derivative does not exist. Because, there's a ruler in this room, because on the one side of the point we have, like a slope of say +2 or something. On the other side, you have a slope of say -2. So at that point between them, they're not going to approach the same number, and that means the derivative does not exist at that point. So here, that discussion is in more detail in last week's differentiability lecture. Here, the absolute maximum occurs at a point where, well, it's at that corner point, it's a point where the derivative does not exist. So f prime does not exist. Now maybe I should say it's undefined. Yeah, I'm going to change that to is undefined. That's probably a better, I guess the real saying, the same basic thing. I'm going to change that to is undefined. Is undefined. That means the same thing. And what about the lowest point? Well, the lowest point on this interval occurs down here at point A, so at an endpoint. And the absolute minimum occurs at an endpoint. So the extreme value theorem is nicely illustrated. Well, the cases of the extreme value theorem are nicely illustrated by those two curves, because they show that the largest y value or the smallest could occur at an endpoint, or they could occur at a point where the derivative is 0, or they could occur at a point where the derivative is undefined. Any questions about those two curves? So before doing some examples, let's just summarize these observations. So I have them summarized right here. We summarized these observations. That type of drawing is nice if you have a graph, but in general, we'll be dealing with functions for which the graph is not necessarily easy to find. So our goal here is going to be to demonstrate the extreme value theorem, meaning we want to find the absolute maximum and the absolute minimum and where they occur. So to find the absolute maximum and minimum of a function f of x on a b1, well, we first need where the derivative is 0, where the derivative is undefined. I guess I should have defined that beforehand. Okay, I'll write it here. Find so those two curves show that where the derivative is 0 and where it's undefined, sometimes they're different because the derivatives aren't the same, but sometimes they share similar properties because they could be at the bottom of a curve like that or the top, or these can both be flipped around. So part 1, find the critical points. And the critical points are going to be those points. I mentioned this in the graphing video that was posted this week. Find the critical points. So I'll just say where f prime equals 0 or f prime is undefined. So first, sometimes in math, I don't like adding extra words to things. So, critical points might seem like we're adding unnecessary words, but in this case and in a couple other contexts, it's convenient to summarize this parenthetical in a couple words. A critical point, where the derivative is 0, where it's undefined. So first, we're going to find the critical points. Step 2. Well, any questions about that definition? Number 2, find the endpoints. Find the endpoints, well, they're going to be given, A and B. So A and B. Step 1 might take a little longer than step 2. So first, find the critical points, find the endpoints. And we know from these observations over here that the absolute maximum and the absolute minimum will occur at a point found in part 1 or a point found in part 2. But to figure out which one is which, we will compare all of the y values. So part 3, compare f of x evaluated at all points, meaning at all points found in parts 1 and 2. So let's look at some examples where we follow that. Any questions? So these examples aren't going to say apply the extreme value theorem. That's, they'll say something more like find the absolute maximum, absolute minimum, where they occur. I don't have any written. Example. Find the absolute maximum and the absolute minimum values of f of x on find the absolute minimum, absolute minimum values. Let's walk into a table. I should move this. Find the absolute maximum and absolute minimum values of f of x too many prepositional phrases in this sentence. Actually, there's only one. Clause. And where I don't like how that's phrased. They probably phrased it better in the homework worksheet. Find the absolute maximum, absolute minimum values, and where they occur. And let's do that one. Let's do 3 of them. Okay. X equals negative x squared plus 3x minus 2 on 0 to 2. And let's do this one. Yeah, let's do this one. F of x is x minus x squared all squared on negative 1 to 1. C f of x equals 1 x plus 1 over x so we have three functions here. We want absolute maximum, absolute minimum. Let's start with the first one. So from this summary, we need the critical points, meaning where the derivative is 0, where it's undefined. We need the endpoints, which are given. And then to find the actual absolute maximum minimum, we need to compare all of the corresponding y values. The largest will be the maximum, the smallest will be the minimum. Let's start with A. So for that function, we need where the derivative is 0 and where it's undefined. So we need the derivative. Derivative here, a couple power rules. We get negative 2x. Derivative of 3x is 3. Derivative of negative 2 is 0. So negative 2x plus 3. And we want where this is 0, so let's set it equal to 0. Subtract 3, divide by negative 2, or add 2x, divide by 2. Either way, you get x equals 3 halves. 3 halves, notice, you substitute x equals 3 halves, so the 2's cancel, you get negative 3 plus 3, so that does work. So f prime here is 0 at x equals 3 halves. F prime here, we also need where it's undefined. But you know, if you have just a polynomial, you really don't have to worry about that. For one like part C, we will mention where it's undefined. So sometimes, and you could say and is never undefined, but if it's a polynomial, I'm okay with just overlooking that observation. But we have all of the points corresponding to our step 1, all of the critical points. X equals 3 halves, and there are none where it's undefined. So now what we need to do is compare the function evaluated at that point, and evaluated at 0, and evaluated at 2. And in doing this, I usually just write them in order. You don't have to, of course. But we're going to need f of 0, f of 2, and f of 3 halves. And we want f, not the derivative, because we're looking here for the absolute maximum and minimum of the function. We want the y values of the function. So notice we're not substituting into f prime. F at 0 is negative 2. F at 3 halves is what? Negative 9/4 plus 9 halves minus 2, and then you take a step back to make sure you don't have something wrong there. Yep. And what does this equal? Well, 9 halves minus 9/4 is 9/4. 9/4 minus 2 is 1/4. This 2 is 8/4. So we have 1/4. And f at 2 is negative 4 plus 6 minus 2. Those add to 0. Equals 0. So here we have 3 y values. The absolute maximum will be the largest. The absolute minimum will be the smallest. So I'm just going to erase this so I have more room here because I don't want to erase the next problems. F at 3 halves happen to be 1/4. Oh, and the other one is 0. So here, now there are a couple ways you could phrase this last thing. You can, circle your answer or something like that. I frequently just write this as a sentence. The absolute maximum is the largest, which is 1/4. So maybe I'll say on 0 to 2, the absolute maximum is what? 1/4, and it occurs at x equals 3 halves, and the absolute minimum is the smallest, which is negative 2, is negative 2, and that occurs at x equals 0. So the question says, find the values and where they occur. The values are the actual largest and smallest, where they occur. these points occur at x values. Any questions about that first example? Okay, let's do the next one. So this part B, we're gonna have to take the derivative. So you could square this out if you want, but if I change this exponent to like a 20 and raising that to the 20, it might be a little tedious. But if you don't want to square it out, you can apply the chain rule to find the derivative. So that's how I'll do this one. And we'll also see in applying the chain rule, it'll make this top equation for part B a little easier to handle. Part B. We have here a function squared. Derivative of a function squared is 2 of them to the first. So the first times by chain rule derivative here. If you wanted to write the details, you would let u equal x minus x squared. Du is 1 minus 2x, or du dx is 1 minus 2x. And dy du is 2u. So here we have the 2u du dx. And we want where this is 0, where it's undefined. Again, this is a polynomial, it's never undefined. But where is it 0? Well, it's already factored almost all the way. It's factored nicely enough that we can set this equal to 0 by setting the 2 pieces equal to 0. It equals 0 when x minus x squared equals 0, or when 1 minus 2x equals 0. This one over here, add 2x, divide by 2, x equals 1/2. So check yourself, substitute x equals 1/2, you get 1 minus 1. So that works. And how about this one? Well, we're going to get 2x values because this does factor further. Both of those terms have an x. And when does this equal 0? Well, when x equals 0, or when x equals 1. And again, this derivative is never undefined. Any questions about finding these critical points? So now we need to compare the function evaluated at those and the endpoints. And notice here, one of those does happen to correspond to an endpoint. That is possible. But here we're going to have 4 y values to deal with. We'll start at -1. Next we have 0. Next we have 1/2. And last we have 1. So we have these 3 and -1. F of 0 in this case is just 0 bounds. I'll write that first because that one's the nicest. F at -1. So we have -1 minus 1 all squared, so 4. -2 squared, which is +4. F at 1, let's do next. F at 1 is 1 minus 1 all squared, so 0. And how about f at 1/2? Well, I guess I can erase this up here. F at 1/2. Well, substitute x equals 1/2. What do you get? You get 1/2 minus 1/2 squared is 1/4. And we square that. That becomes 1/4 squared, so 1/16. 1/16. So we have our 4 values here. The absolute maximum is the largest. The absolute minimum is the smallest. In solutions, it's very common that I consolidate this in a sentence, but you could summarize that by pointing out something like this. Right there, we have the absolute maximum. The largest is 4. And what about the minimum? Well, notice here we hit 0 twice. So the absolute minimum is 0. The absolute minimum is 0, and it occurs at 2 different points. And that can happen, you know, if you have a curve like this, it could hit the same lowest value twice. Any questions about this second one? This isn't necessarily what this curve looks like. That's just to illustrate one of these values. The lowest could be hit multiple times. So any questions about what was that, part B? Let's go to part C. Here, we need where the derivative is 0 and where it's undefined. So first we need the derivative. I'm just going to rewrite this up here so I can erase that. Well, the derivative of x, just 1, derivative of 1 over x, negative 1 over x squared. Why is that? Well, more on that in a moment. After this example, I'm going to make a remark that'll be rather useful for computation purposes. But how did we get that derivative? Well, using the power rule. Derivative of 1 over x, well, 1 over x, maybe I'll write it like this. 1 over x is the same as x to the negative 1. Derivative of x to the negative 1 with the power rule is negative 1, x to the negative 1 minus 1, so negative x to the negative 2. And you know, for a question that just says find the derivative, you know, that answer is perfectly fine. But we are going to do a few applications of the derivative in which writing this in its fractional form will be will make the future simplification and computation a little easier. And the fractional form of this is, you know, just put the negative exponents, change which side of the fraction something is on. So that's really an x squared in the bottom, and it's negative. So you know, this derivative shows up enough times that I think it's worth practicing jumping straight from 1 over x to negative 1 over x squared in its fractional form. And it showed up, well, it's going to show up in the video next week. It'll show up in a couple other applications. Any questions about finding this derivative? We want where it's 0. We want where it's undefined. So where is this 0? Well, let's set it equal to 0. It equals 0 when 1 equals 1 over x squared. We'll bring this to the other side. Multiply by x squared equals 0 when x squared equals 1. Well, when is that solved? X equals positive or negative 1. So right here we have where the derivative is 0. We have a fraction here, so we're also going to need where the derivative is undefined. If you have a square root, you'd also have to worry about where it's undefined. So I'll just say, and it's undefined. Maybe I'll write it over there. And f prime is undefined when, well, when is it undefined? It's when the denominator equals 0, which in this case is when x equals 0. We have our critical points. I thought there was a 4 in this one. I must be thinking of a different example. Any questions about finding those? Oh, there is a 4. Any questions about finding these values? so now we just need to compare our function at all of the values, but notice, I guess I'll draw this over here. This function cares only what happens from 1/5 to 4. So say 1/5 is here, say 4 is here. The only part of the curve we're looking at is 1/5 to 4. So if we have, this isn't a drawing of this curve, if we have a critical point outside of this interval, well, that's not going to matter, because all that matters is what happens between 1/5 and 4. So notice here, the x value 0 outside the interval doesn't matter. The x value -1 outside the interval doesn't matter. But what does matter is what occurs on that interval. We need the endpoints, and we need the critical points within that interval. 1 is within that interval. And the endpoints 1/5 and 4 are the endpoints. F at 1, I'll do that one first, is 1 plus 1, which is 2. F at 4, 4 plus 1/4. You could write this as 17/4. You could write it as 4 1/4. I'll just leave it like that. F at 1/5. What's F at 1/5? Well, x equals 1/5, so that's 1/5 plus 1/1/5. 1/5 plus 5. So F at 1/5 is 5 plus 1/5. You could write as 26/5. The reason I'm leaving, these sort of mixed numbers here is for the next step. Comparing 17/4 and 25 or 26/5 might be a little, might be inconvenient, but comparing something a little more than 5 to something a little more than 4 is, that's obvious which one is larger. So what is the largest? Well, the one a little more than 5 is the largest. So maybe I'll just do it like I did the second one. So here we have the absolute maximum value, 26/5 occurring at x equals 5, and the smallest, well, 2 is less than the other one. So here we have the absolute minimum occurring where x equals, when x equals 1. Any questions about that one? Okay. So there are a couple extreme value theorem questions. They tend to follow similarly to these. But let's next look at some consequences of chain. Let's start with, what time do we have? 1:37. Let's start with a quick consequence, and then let's go to a couple less quick consequences. Where is this in my notes? Oh, there it is. We have here inverse functions. We don't have a formula for the derivative of inverse functions. Now let's do it over here. Let's say consequences. We're actually going to look at 4 consequences of chain rule. Related rates, which is listed separately from consequences of chain rule in the syllabus schedule, is still a consequence of the chain rule, but I did block it off. Consequences of chain rule. Let's first look at the derivative of inverse functions. And the notation for the derivative of the inverse is going to be, well, there's the inverse. The derivative, we're going to throw a prime on that. And to separate the inverse -1 from the prime, I'll put large parentheses there. And it's a function of x. Derivative of inverse functions. How can we find this? Well, we can use the chain rule. Why can we use the chain rule? Well, let's see. Recall, we're going to make two recollections. First, the definition of the inverse function. Inverse functions satisfy which equation? Well, an inverse is so that f composed with f inverse brings you back to x always. So inverse functions satisfy f inverse composed with f. I'm going to write it. So sometimes you see composition with the circle. I'm going to write it as the actual computation of the composition because that's what we're going to use here. Inverse functions satisfy that the inverse and the function, in a sense, cancel. And that can happen in either way. Either way, they cancel, in a sense, and leave you with just x. So that's one definition of an inverse. And another, you could say the curve flips over x equals y. But there's our first recollection. Further recall the chain rule statement. I'll just say further recall the chain rule. And here we're not going to use the u substitution way. I am going to write out the composition. Because here, remember, the chain rule tells you how to take derivatives of compositions. And here, in both cases, we have the definition in a composition form. It's going to fit here. So the chain rule says the derivative of a composition is the derivative of f inside alone times the derivative of that inside function g. Any questions about those two recollections? Okay, so how can we use these to find the derivative of an inverse function? Well, apply the chain rule to, I'll just say, yeah, okay, to the equation. I'm going to use this second one. The eventual algebra works out much nicer. And we'll see why in a moment. Apply the chain rule to this composition here. We'll apply the chain rule to that entire equation. And what do we get? Well, let's put a colon. What do we get? Well, the left side is the derivative of the composition. So let's follow our notation here. We have two pieces, this piece and that piece. Derivative of the outside. The inside alone times the derivative of the inside function, which in this case is f inverse. So times the derivative of f inverse. This is one of those many situations where I find online paper to be much more useful because with lined paper, I find it much harder to size parentheses accordingly. And I really like to make large parentheses to help keep myself organized. So the left side becomes this when you apply the chain rule. I really could have said take the derivative of, but I guess applying the chain rule will make it look like it follows from this a little more clearly. So we did that to the left side. Do it to the right side. Derivative of 1, or derivative of x with respect to x is just 1. Any questions about getting that equation? There is a good deal of notation to follow, but notice what happened in doing this. We were looking for the derivative of f inverse. And look what we have right here, the derivative of f inverse. So the chain rule causes what we wanted to show up. So all we need to do is solve for this. Maybe I'll say solve for this, which is what we want. So the derivative of f inverse equals 1. How do we solve for this? Well, how do you solve how do you solve 2x equals 1 for x? You want to solve for x, you notice there's a 2 in the way, so you get rid of the 2 by dividing. If we want to solve for this blue underlined quantity and all of that mess is in the way, how do we solve? We divide by that quantity. Divide the left by that quantity, you get that. Divide the right by that quantity, you get 1 divided by f prime of f inverse of x. I'll put a square around this. Any questions about finding that formula? It's a little notation-y, but you know, when I have a lot of notation all over the place, one thing I like to do to help is use parentheses well. And you know, notice in all of these, I make this of x pretty small because that's kind of, well, it's not completely unnecessary, but it is a little in the way. So I made it as small as possible. But do compare going from here to going from here to here, and use parentheses as well. Any questions about that? In this summer class, you know, I decided to overlook inverse trig functions. This formula is used to prove derivative rules for the inverse trig functions. You know, we're not covering inverse trig functions in this summer class, but you know, I would like you to know how to get here. Something like, you know, show why this formula is true is definitely a question that
Do we have to know inverse trig functions for Calc 2?
Might. I'd have to ask one of the other and I had, so that there's, for the Muhlenberg Calc 1 class, there is a list of definite topics, a list of optional topics. And inverse trig was in the optional topics, actually, which would suggest they are not necessarily required for Calc 2. Any other questions about this one? So let's look at another consequence of chain rule. We're going to call this next one implicit differentiation, but to get there, let's make an observation. Let's move it over so I can write something next to it. Right here, we have a circle. Let's call it a circle of radius 5. A circle satisfies the equation x squared plus y squared equals the radius squared. So let's say this one's radius 5. So x squared plus y squared equals 25. Let's move it lower. Circle radius 5. X squared plus y squared equals 25. This right here is not a function by the vertical line test. So if we want say slopes of tangent lines in general, if we want a formula for slopes of tangent lines, we can't solve this for y and then find dy dx. So notice a circle is not a function. Function. And because of that, we can't find dy dx. So what does "it's not a function" actually mean? Well, we can't you can solve that for y by taking by subtracting x squared and taking square roots. But when you take the square root, you would wind up with a positive and a negative, meaning y, if you tried to solve it, would equal two different things. And when that happens, we say we can't explicitly solve the equation x squared plus y squared equals 25 for y. We can't explicitly solve that equation for y because we would have to make a choice on the square roots, and that would split the curve into two pieces. Now the top half and the bottom half. So you could, if you wanted, if I said find slopes of tangent lines, and you could say the top half of the curve is, the top half of the curve is y equals positive root 25 minus x squared. The bottom half of the curve is negative root 25 minus x squared, and then go from there. But we can use the chain rule to help us find dy dx. Let's say we can, however, say y is implicitly defined in terms of x. Y is defined implicitly in terms of x. So being written or explicitly in terms of x means you can say y equals something, and it is a function. But saying it's implicitly defined in terms of x means it is written in terms of x, but we can't solve it implicitly. So we can say, in this case, y is defined implicitly in terms of x, and I'll say comma, and I'll go up here, satisfying the equation x squared plus y squared equals 25. So with this circle example, you could break it into two functions and go from there. With the next example, we won't be able to, meaning you could say y equals positive, y equals negative, square root, and so on, and go from there. That is a lot more work than is necessary, and we'll see why in a minute. When we have an equation where, let's say, x and y, where y is defined implicitly in terms of x, we can use the chain rule to find dy dx. So maybe I should bullet these. Bullet 1, a circle is not a function. We can't explicitly solve for y. We can say y is defined implicitly, satisfying that equation, and in that case, we can use the chain rule to find dy dx. So let's do that with this example. Example. Find, let's illustrate where the chain rule shows up. Find dy dx here. Well, recall the structure of the chain rule. And this actually showed up in part B of the last example. Well, let's do it and then recall the structure. Find dy dx. Well, here we have our equation, not solve for y. What we can do is differentiate, meaning take the derivative, with respect to x. With respect to shows up a few times in calculus, so we can abbreviate WRT. With respect to x. That's a standard abbreviation in math too. Differentiate with respect to x. What do we get? Well, derivative of x squared with respect to x is 2x. Derivative of y squared with respect to x. Well, we know here from this equation that y is implicitly not a function, but it's implicitly defined in terms of x, meaning we can think of y, maybe I'll write it at the top of the board. We can think of y as having a bunch of x's. And that's okay. A bunch of x's. And that's a little informal. What does that mean? Meaning in this case, we can think of y squared as being a lot of x's bunch of x's all squared. And when we have a large quantity of x's all squared, we can find that derivative using the chain rule. The chain rule says the derivative of something all squared is 2 of them first power, 2 of them to the first power times that inside case the bunch of x's times their derivative. The chain rule says derivative of a large quantity of x's squared is 2 of them to the first times their derivative. What does that look like here? Well, we have y squared, so we would have 2y to the first times the derivative of y, which is dy dx. Any questions about dealing with the y squared piece? Now, well, let's finish this equation. 25 is constant, so its derivative is 0 with respect to anything. Now, let's finish this, then I'll say the 2 things I was about to say. Our goal here was to find dy dx. And notice in that equation, there is a dy dx. So we can solve for dy dx. So we solve for dy dx. And what do we get? Well, we get 2y dy dx equals negative 2x, divide by 2y, and you get dy dx equals, the 2's cancel, and you get negative x over y. Any questions about this example here? Okay, I have 3 things to say about this example. First, notice there is a y in our answer. When we were doing chain rule, just the derivative computations with the chain rule, we didn't leave u in our answer because we were able to simplify nicely for u. Here, we can't solve that nicely for y. And when that happens, we can leave y in our answer. 2 other things. Sometimes, and when I took Calc 1, and a lot of students I've had in the past would write this as just y prime, meaning you can interpret this as a find y prime, and instead of writing all those letters dy dx, just write a y prime. You can do that if you want. Now, the reason I don't is, now our goal here is to find dy dx, and when I write the fraction, it kind of makes the dy dx piece pop out to me. But if you want to write y prime, that's certainly okay. But do be careful that you don't interpret that as a y to the first when you're going through the work. One other thing, let's just look at these 2 equations. So over there on the other side of the board, what I erased was kind of a long argument for finding the derivative. Is there a simpler way of viewing it? Well, there is a simpler way of viewing this differentiating with respect to x. When we differentiate with respect to x here, you can think of it as doing the derivatives all normally. But whenever you take the derivative of something with a y, throw a dy dx or throw a y prime on it. So notice doing the derivative of the x piece, we got 2x, and that's our normal derivative observation. But when we did the y's, a dy dx showed up. So you can think of it as, every time you take the derivative of a y piece, throw a dy dx on it, or throw a y prime on it. But it does show up by the chain rule. Any questions about this first one? Okay, let's do another example. Well, let's use that. Find equations for all lines tangent to this curve, same curve, tangent to x squared plus y squared plus 25, when x equals 3. Let's make the numbers work out nicely. When x equals 3. Well, we need equations for tangent lines. Equation for a line, we need a point, and we need a slope. Well, here we have our derivatives. We can use this to find the slope, but notice we're going to need the y values. Before even thinking about slope, I'm going to find what y value corresponds to x equals 3. So to find points, well, point more than 1, which in this case there is more than 1. Let x equal 3 in this equation, and you get 9 plus y squared equals 25. We need the y values, subtract 9, and then take a square root. Positive 4 squared is 16, negative 4 squared is 16 as well. So when x equals 3, we have 2 different y values, meaning we're going to have two different tangent lines, one corresponding to that point and one corresponding to this point. Notice both of them do satisfy x equals 3. Oh, and we also need a slope over here. Any question? Well, in this case, we had two different points, and in the directions, it doesn't say there are 2 points, it says all of them. The algebra will work out, you know, in a way you've seen before. Let's just say, you know, if there's one like this, you know, it could look like that. And in this case, 2 points show up. Any questions about finding these points? So now we need the slopes. Well, the slope, remember, is given by, it's still given by dy dx. And what is it? It's negative x over y in both cases. Negative x over y here is negative 3/4. And over here, dy dx is negative x over y, which here is negative 3 over negative 4, just 3/4. We want the equation, so here we get y plus 4 equals 3/4 of x minus 3. Over here we get something similar. Y minus 4 is negative 3/4 of x minus 3. You don't have to solve for y. Any questions about this one? Now, this curve is a circle, so we could show what this looks like, and I will show what this looks like. Where do I erase? I guess I'll show it up here. Now I'll show it. I have to erase some of that. I'll leave that in case it's not there. What do these tangent lines look like? Well, we have a circle. That's an awful circle. We had a circle. That's better. And we wanted x equals 3. X equals, it's a circle of radius 5. So this point out here is 5, 0. That's going to get in the way of my tangent lines. Circle of radius 5, I'm going to label this point. Make it clear it's radius 5, and that point will be out of the way. So the one tangent line is going to be up here when x equals 3. It'll look something like that, and notice we do have a negative slope for that point. And the other tangent line will be tangent at that point. And it'll look like that. And that negative 5, 0 point is just there to make it clear it's a circle of radius 5. Any questions about that? Let's do one more of these implicit differentiation problems. Let's throw a product rule somewhere in here. So in this one, this circle one, if you didn't have this implicit differentiation technique, you could have said y equals the positive square root of 25 minus x squared, y equals the negative. You could have found the derivatives there. And notice in each case, you would have gotten one of these tangent lines if you had to find tangent lines. For this next equation, you can't solve it explicitly. You can't even solve it, well, in a lot of pieces you can solve it for y, but not convenient. So let's do find dy dx here. for this one, I will use our observations where we do the derivatives of each piece normally, but we throw a dy dx on when we take the derivative of something with a y. Let's see, I want product rules, let's make it 2 plus, let's see, we have a trig, so what did I put on the worksheet? Okay, let's do one like this. Y cubed, let's see, we have a tangent. Let's throw a negative here. Cosine of x. So find dy dx here. Notice we have an equation with lots of x's and y's. We can use our implicit differentiation technique to find some dy dx's, and then we can solve for that. So differentiate with respect to x. Differentiate is also a very long word, diff. Differentiate with respect to x, meaning take derivatives normally, but throw dy dx's on when you take derivatives of y's. 4x to the 5th, derivative is 20x cubed, not cubed. 20x to the 4th. So 5x to the 4th times 20. Differentiate with respect to x. We have here tangent, a tangent function. The derivative of a tangent function is a secant squared. So we have secant squared. I'm going to put parentheses on the y. So we have the derivative of a tangent function is a secant squared function, but differentiate a y piece with respect to x, you need to throw a dy dx on that. Any questions about the left side of that equation? So the x's are treated normally, the y's are treated normally, except you throw a dy dx on. How about the right side? Well, 2 is a constant, derivative is 0. And then we have this piece. We have y cubed times cosine x. So we have two things multiplied, meaning we're going to have a product rule. What does the product rule say? Well, we need the derivative of one times the other plus the one times the derivative of the other. Let's do derivative of this one first. Derivative of y cubed. Do it normally, 3y squared. Use the chain rule, times dy dx by the chain rule. Now, in your work, you don't have to write this multiplication dot. I am using it here just to well, to make it clear, there's a dot there, there's a multiplication there. And why is there a multiplication? Because of the chain rule. So the derivative of y cubed is here. Follow the product rule now. We have cosine of x, derivative of the first times the second plus the first. I'm going to write the plus in a moment, but it's going to look like a negative. Plus the first times the derivative of cosine. Derivative of cosine is negative sine. And this is the correct equation here. Now, on this left side with the product rule, notice there's no dy dx on this piece over here. Why is that? Well, which derivative did we take to get over here? We took the derivative of just cosine of x. There are no y's in there. And the dy dx's, or the y primes, show up when you take the derivative of a y with respect to x. So in the product rule, a dy dx will show up when you differentiate the y piece, and it won't show up when you don't. Any questions about that? Okay, so now we want to solve, or we wanted to find dy dx. So now we have to solve for it. How can we solve this? Well, I like to, in one of these with a lot of terms, I like to use underlining to my advantage. I like to observe which pieces have dy dx's and which pieces don't, and just underline them. And then what we do, well, if you solve, say, you wanted to solve that equation for x, you put all the x's on one side. What do you get? X equals 1? No, you get x equals, what do you get here? -1. Solve an equation like this for x, put all the x's on one side, put all the numbers on one side, and divide. We do the same thing here. Put all the dy dx's on one side, put all the non-dy dx's on one side, and divide. What does that look like? It looks like I'm going to run out of room. So I'm going to put this piece on the other side, just so the negatives work out nicely. And I'm going to put this piece on the other side. And what do we get? 3y squared dy dx cosine x negative secant squared of y dy dx. So put all the dy dx's on one side, put all the other things on the other side. And now what can we do? We can factor and divide. Well, any questions about that first step in simplification? Okay, so what can we do next? Well, everything on the right now has a dy dx. So you can factor dy dx out. And you're left with 3y squared cosine of x minus the secant squared of y. If you factor that out, I guess I can erase this. That won't ruin anything. So you can factor dy dx from the right. And now you can solve for dy dx by dividing by that piece. So dy dx equals, divide by that. So it's this. Divided by that. I'll put a square. And notice there are x's and y's in our final answer. Any questions about this one? So with an equation where it's, equation like this, I'm not going to ask you to find tangent lines. I'm not going to, well, I could ask you to find a tangent line, but in that case, I would give you the x and the y. Because solving this full equation, given an x, solve it for y, that's, not something I would have you do. But if I did say, here's an x, y, find the tangent line, well, you have the point, and you use this for the slope. Y equals 0 could be used there because, well, I'm not going to ask you one where it's like that. If you have to find tangent lines using implicit differentiation, it'll probably be more like the circle one, or on the worksheet you have an ellipse one. But any questions about this last example? There are a couple of those on the worksheet, but let's now look at a third consequence of the chain rule. Let's look at it on this board. And again, for this one, we're going to make some recollections. What's this? 3. Logarithmic. 3 meaning third list in the list of consequences of chain rule. Logarithmic differentiation. What is logarithmic differentiation? Well, we'll see. But to build to this, let's make 2 recollections. I think I just realized recollection is the noun form of recall, isn't it? Huh. I would realize that more right now. Recall. Remember, we have this. This is going to be bulleted. So that's a bullet, not a multiplication. That's not going to fit. We have another notation for taking a derivative, d by dx, d over dx, of a function. Recall, the derivative of x to the n is what? Well, it's x to some number. It's nx to the n minus 1. And this is the power rule. Also, derivative of b to the x. So in that first case, x was in our base, and the exponent was a number. In the second case, a number is the base, and x is in the exponent. But we know how to find this derivative using the logarithm rule, general exponential rule. The derivative is of b to the x is b to the x times the natural log of b. So I'll call this general exponential rule. So the first case, we have x's in the base and numbers in the exponent. The second case, we have numbers in the base and x's in the exponent. So the question would be, what if you have x's in the base and x's in the exponent? Well, notice first, these 2 rules won't apply because these assume either the exponent's a number or the base is the number. That's a question mark in case that dot doesn't show up. There's a dot there. Question mark. What is this derivative with x's in the base and x's in the exponent? Well, we can't use those 2 rules up here. But what can we do? Well, let's see what we can do. What can we do with that? Well, we can use a logarithm. How is that going to help us? Let's say introduce. Let's see. So to this equation, x to the x, we can introduce a logarithm. And what would that do? Well, if you throw a logarithm on there, we can use the logarithm rule, which says an exponent comes out in front. We can introduce a logarithm to turn, let's just say it a little informally, x to the x into a product. If we throw a logarithm on x to the x, the logarithm properties will turn that exponent into a product. Let's look at what we mean by that. Example, find dy dx for, I really should start at the top of the board for this. I want to leave those over there. Actually, this one will work out. Find dy dx for y equals x to the x. So we have our equation y equals x to the x. We want dy dx. Well, up here, this says throw a logarithm on it, and that exponential, well, not exponential, that right side is going to be a product. So throw a logarithm on the right side. Well, if you do that, you have to do it to the left so that they're still equal. Logarithm of x to the x. And using the logarithm rules, that exponent x comes out front. And now the right side of that equation is written as a product. Exactly, have to fix this. Any questions about what we did in that equation, in that line? We threw a logarithm on our function and it got rid of this form which looks exponential and turned it into a product. But now look at what we have. Well, I'll just say so. I'm going to bypass that middle line. The logarithm of y equals x times the logarithm of x. And right here, we have an equation relating y and x, where y is implicitly written in terms of x. So in this case, we can explicitly solve for y. But we saw that none of the derivative rules we had applied when it was explicitly written in terms of y. So what we can do, throw a logarithm on it and apply implicit differentiation, because now we can take all these derivatives. So let's do that. So I'll say differentiate implicitly with respect to x. And what do we get? Well, on the left side, we'll do that in a moment. On the right side, we have a product. Use the product rule. Derivative of x is 1. So derivative of x is 1 times log x plus, well, maybe I will write the 1. 1 times log x plus the first times derivative of the second. Derivative of log x, remember, is 1 over x. And there are a lot of 1's all over here, so this does simplify kind of nicely, this right side. Right side, x times 1 over x here, that's just 1. 1 times log x is log x. So the right side does simplify nicely. Any questions about the right side? There weren't any y's on the right side, so we just took the derivative normally. What about the left side? Well, differentiate with respect to x. Do the derivative normally. Derivative of log of something is 1 over that thing. Then throw a dy dx or throw a y prime. So we have 1 over y, dy dx on the left. That dy dx does show up by the chain rule, equals log x plus natural log x plus 1. Any questions about getting that equation over there? Okay, so we wanted to find dy dx. Well, there it is. But there's 1 over y on it. So we have to get rid of this 1 over y. So dy dx equals, multiply the left side by y, that goes away. Multiply the right side by y, and what do you get? Well, I'm going to take advantage of the fact that I have a chalkboard and eraser here. I'm going to write y like that. Multiply left side by y, you have dy dx. Multiply the right side by y, you have y. times that. So y times natural log of x plus 1. But when you can get rid of the y, you should get rid of the y. And here we can get rid of the y because y is just x to the x. In the last example with that 4x to the fifth and the tangent, you couldn't solve that for y, but here you could. So just replace the y with the x to the x. Any questions about this one? Okay, so what did we do here? We threw a logarithm on it, it turned it into a product, and then we differentiated implicitly. These, that fall under category 3 here, this type of term on the left side is going to show up, in all of them because it's just going to be a log y equals something. But any questions about them? Okay, let's do another with more than just x. Now, well, let's write it and then say what I was about to say. Find dy dx for this one. Well, we just did one with cosine, so maybe I should change it to, no, I'll leave it as cosine. Cosine x to the x squared. Now you may be wondering, we use a natural log here. Would other logarithms work? And yes, they would work, but the derivative of a general logarithm, remember, is 1 over x times that constant. So in our computation, that constant's going to show up all over the place, and it's eventually going to cancel out. So, if you don't have to deal with extra constants, then, you shouldn't. So a different logarithmic base would work, but the natural logarithm is the one that will make our equations look the nicest. If you had extra log 5s or something all over the place, this equation would look much worse. So let's just use a natural logarithm. Example. Find dy dx for what? Y equals cosine of x all to the x squared. Now, first of all, that rule over there, that previous example doesn't give a general rule. Meaning it doesn't give you a rule that you can eventually use a substitution and apply chain rule on. Because if you have x's in the base and the exponent and you let u equal something, like say in this example, say you let u equal cosine of x. Well, then you'd have u to the x squared. And this is still a function of x. The previous chain rule problems we've done, the chain rule works with the u substitution only when you can get rid of all of the x's. So that first example doesn't define a general rule, but the process does work in general. Meaning, for a function like this, where again we have x's in the base, we have x's in the exponent, we can throw a logarithm on, differentiate implicitly, and then solve for dy dx. So let's do that here. Logarithm of the left, logarithm of the right. Logarithm of cosine x all to the x squared, but the x squared comes out front using the logarithm properties. Differentiate with respect to x. On the left side, you're again going to get a 1 over y times dy dx. On the right side, again, we'll have a product rule show up. Derivative of x squared is 2x. minus x squared tangent x. Where did that come from? Well, where did it come from? I wanted that equation to look nice, so I'm going to do side work to get that. Where did that come from? Well, I'm going to write so y equals whatever it equals up there, but the side work. So for this, we did derivative of x squared is 2x. And then we have the x squared on the other side. So I'm claiming here derivative of log cosine, natural log cosine x is negative tangent x. Why is that? Well, we started with log of cosine x. Derivative of that, 1 divided by the inside times the derivative. So here, if you wanted to use substitution, u equals cosine. Derivative of log u is 1 over u. Du dx is negative sine of x. Derivative of cosine is negative sine. And if you left your answer like this, I would not deduct. But sine over cosine can be written in fewer arm strokes pretty conveniently, so I usually do simplify it. Sine over cosine is tangent, and then there's a negative on there. So product rule, 2x times the second plus the first, which is x squared, times derivative of the second, negative tangent, gives us negative tangent. Any questions about that, where that equation came from? So we wanted dy dx here. Well, dy dx is there. Oh, we're not saying so y. So dy dx equals dy dx, multiply the left side by y, dy dx, multiply the right side by y, you have y times all that. All times y, but we can rewrite y in terms of x. And maybe I'll write through that step in this case. Dy dx is that, replace y with cosine x to the x squared. Because we can write y explicitly in terms of x. 2x cosine x, 2x log cosine x. Any questions about that one? So those, really the implicit differentiation and the logarithmic differentiation problems, the resulting answers could look very intimidating. This has lots of algebra, lots of x's all over the place, and logarithms. But if you break it down step by step and notice what we're really doing is using previously known derivative rules with one extra observation. Well, 2 extra observations in this case. A logarithm helps, but then we differentiate implicitly. It becomes much less intimidating looking. And when you have x's in the base and x's in the exponent, this general process will work. Logarithm turns into a product, differentiate implicitly, multiply by y. So any questions about that? Okay. Now I just posted on Canvas, meaning an hour and 40 minutes ago, a document called logarithmic differentiation type 2 example or something like that. There are other equations that we can throw logarithms on, and it makes derivatives look a little, well, potentially take less time. I'm not gonna ask one of those problems, so I'm gonna go over it tomorrow, toward the end if there's time. But there is a document called Logarithm Differentiation Part 2 or Type 2 problem. It's 1 page. I will discuss that in detail during tomorrow's class because I'd rather cover a little more that'll be on the exam on Monday today than I'd rather that than push off a couple things till tomorrow. So I will discuss that tomorrow, but this is one type of logarithmic differentiation, has x's in the base and x's in the exponent. I'm much more concerned with that than the other, but I will discuss the other tomorrow because it is useful. But for now, let's go on to related rates, which will be our fourth consequence of chain rule. It'll be our last consequence of chain. And I personally believe the hardest consequence of chain rule. Related rates. Well, we first recall that our derivatives measure rates of change, especially when we have functions of time. Now the derivative, we had a position function whose derivative was velocity because the rate of change of position is velocity. And we're gonna keep that in mind for these. Maybe I'll illustrate this with an example rather than theoretically. Yeah, let's illustrate this with an example. And during this example, I'll point out some of the theory. This example is going to take a moment to write. These related rates examples, I'll take a moment to write. Example. A 10-foot ladder is leaning against the wall. Okay, it begins to slip so that the bottom of the ladder is moving at a rate of 3 feet per second. It begins to slip so that bottom of the ladder is moving a rate of 3 feet per second. 10-foot ladder is leaning against the wall, begins to slip so the bottom of the ladder is moving at a rate of 3 feet per second. The question will be, how fast is the top of the ladder moving? When, what? So here we have, I guess I'll better to illustrate than to just do it with an arm motion. How fast is the top of the ladder moving when the bottom of the ladder is 6 feet from the wall? I'll give you a moment to write that down. We'll be able to get through probably 3, maybe 4 examples of these, depending on which ones we do. So a 10-foot ladder leaning against a wall begins to slip so that the bottom is moving at a rate. How fast is the top moving when the bottom is 6 feet from the wall? So with these related rates questions, well, we'll see what we mean by rates in a moment, but before that, I find it very helpful, at least with problems with some of them to draw out a picture. For the second one, the picture may not be helpful, but for this first one, it will. So what does our situation here look like? A 10-foot ladder is leaning against a wall. So let's draw it. There's a wall, there's a ground, there's a ladder. It's 10 feet. So that's the most basic picture of what we have. 10-foot ladder leaning against a wall. And it begins to slip so that the bottom is moving at a rate. So in these, it'll be convenient to label our variable quantities. So this ladder begins to slip. I guess I have that yardstick still. So it begins to slip. It's like this. Then it begins to slip. You can imagine it's small. It begins to slip. What are the quantities that are changing? Well, this distance here is changing, meaning that horizontal distance, the distance from the wall to the bottom of the ladder, is a variable quantity. Let's call it x. This vertical quantity, the distance from the ground to the top of the ladder, is also changing. Let's call it y. And I tend to prefer x and y because I'm most used to doing calculus with x's and y's. And once we have this picture, we can turn this question into a calculus question. So what is the question saying? Maybe I should put this first. We'll draw a picture. 2, we will, well, 2, you could get an equation from the picture. So 2 and 3, well, I'll just say, I'll write 2 over here, actually. 2, translate question into calculus. What does that look like here? How do we translate it into calculus? Well, we use our picture. How fast is the top of the ladder moving when the bottom is 6 feet from the wall? So how fast the top of the ladder moving is a rate of change. The top of the ladder is moving at a rate of a change in y given a change in time. And we're looking here at instantaneous rates because it says when the bottom is 6 feet from the wall. So this ladder is sliding down the wall. At some instant, the bottom is 6 from the wall. At some instant, x equals 6. And this question is saying, how is y changing when x equals 6? Well, how does y change? Well, y changes as y is changing. Y is changing as time is changing. So this question is asking, how is y changing as time is changing? And derivatives tell us how we can see that instantaneous rate of change. We can use a derivative to give us an instantaneous rate of change. So this question is saying, right, and how fast is the top moving? It says find dy dt. Any questions about why this is asking us to find dy dt? So here we are looking for an instantaneous rate of change. So we want dy dt at an instant. So we can further translate this to say find dy dt when a bunch of things happen. In this case, what happens? When the bottom is 6 feet from the wall. What's measuring where the bottom is? X. So when x equals 6. And I did write that a little above when for a moment. When x equals 6, I'm going to leave a gap under x equals 6 and say further and. What else is given? Well, a 10-foot ladder, that's already incorporated. What else is given? The bottom of the ladder is moving at a rate of 3 feet per second. So the bottom is changing at a rate of 3 feet per second. So the rate of change of the bottom at all instants is 3. I'm just gonna throw units on these, I guess. I like to throw units on the rates because it helps. I don't know, the units show up in the notation for the derivative. Now, another reason to use the fractional notation is because it looks like the units of a rate of change. So this question is really saying find dy dt when x equals 6, something else, and when dx dt is 3. Now, what is this something else? Well, we will need it eventually. In one of the examples, I'll leave a blank and then find it afterwards. But right here, when x equals 6, y does equal 8 from a 6, 8, 10 triangle. And we'll need that in a moment. But once we've translated that question, this question, we can ignore all of these words and jump straight to equations. Now, we don't have an equation yet. Step 3, find an equation. And step 2 and 3, it may be useful to find the equation first, it may not. I'll write it like this, I guess. Maybe I should have written the equation first. Find an equation. Well, we have a right triangle, so the Pythagorean theorem says x squared plus y squared equals 10 squared. X squared plus y squared equals 100. Any questions about finding the equation? Finding this y value, you could also jump down to that equation and take the positive square root because these are distances. Any questions about that? Maybe I'll say differentiate. So differentiate and solve. Differentiate what and solve? Well, we have the equation x squared plus y squared equals 100. Differentiate. Well, notice in our translation of the question, we have 2 different derivatives showing up, dy dt and dx dt. How can they matter? How come they matter? Well, they matter because they're giving us instantaneous rates of change. But what are they actually telling us? They are telling us that x and y, these variables, are actually functions of time. X is changing as time is changing. Y is changing as time is changing. So we can differentiate with respect to time. X and Y are functions of time. So I'll say here, differentiate with respect to time, which is t. And now we have x being a function of time and y being a function of time. To differentiate, we would use the chain rule. And notice here, a rate is going to show up in each case. A derivative is going to show up in each case because x is a function of time and y is a function of time. Well, a non-constant function of time. So a dx dt shows up, a dy dt shows up, both by the chain rule. You can think of x as being a bunch of t's all squared. You can think of y as being a bunch of t's all squared, and use our implicit differentiation observation, but here we're differentiating with respect to time. Any questions about that one? Well, about that, where that equation came from? Okay, so it says differentiate and solve. Once we differentiate it, all we have to do is go back here, substitute our numbers and solve. We want a dy dt. Well, there's dy dt. So solve, what do we get? X equals 6, dx dt equaled 3, y equaled 8, dy dt was what we wanted to solve for. Equals 0, solve for dy dt. And I'm going to reference that picture in a moment. And what do we get? Well, the 2's cancel. I guess I'll leave them there. You get 36 plus 16 dy dt equals 0. So dy dt equals what? Subtract 36 divided by 16. 2's cancel. You get 18 over 8. So 9/4 with negative. Negative 9/4 feet per second. Any questions about that? Okay, I guess we'll only get to go through one more example, but that's okay. It'll be, well, it'll be any questions about that first example? Now notice our dx dt was positive and our dy dt was negative. That the given dx dt was positive. And why would that have been? Well, while I'm writing the next question, think about why that would have been. Dy dt is negative, dx dt in that example was positive. Next example, a spherical balloon is being inflated at a rate of 3 cubic feet per second. How fast is the radius changing when the diameter is 14 inches? But before that, why was dx dt positive, dy dt negative over here? Well, remember, with velocity, walking forward is positive, walking backward is negative velocity, meaning when you walk forward, your change of position is in the positive direction. When you walk backward, your change of position is in the negative direction. So here, as the balloon slips down, notice x is getting larger than the balloon. As the ladder slips down, the x value is getting larger and the y value is getting smaller. And that's reflected in these rates. Right here in this next example, a spherical balloon is being inflated at a rate. How fast is the radius changing? So here it may not be that useful to draw a picture because it's just a sphere, but we can translate the question. So I'll say here, question is asking what? Well, how fast is the radius changing? So find dr dt, the rate of change of radius, when the diameter is 14. Diameter doesn't really matter much. So when radius is 7. And it's being inflated, so it's telling us how the volume is changing. is 3 cubic feet per second. Any questions about translating that question into calculus? Our equation for volume of a sphere is given by that. And, well, we'll go over this one tomorrow. The first example took a little longer than I expected. If you want to check your work for this one, the answer is 3 over 196 pi. But we'll start tomorrow with that example, then we'll do another related rates, and we'll get through everything that's on the Thursday schedule. That won't be a problem. But any questions? Well, any questions right now? Now, I do have an office hour in a moment, and I'll send a link in a moment. But it is definitely a good idea, since we do have a test coming up, to practice some of these problems. You know, especially like on the worksheet, all of the number 1 questions, number 2, and number 3A. 3B and D might be a little harder without going through these examples, but you know, also you can do number 7 and 8 with what we've, oh no, not just number 7 with what we've done. So I will send a link for an office hour in a moment.